Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. The Earth beneath you is not at rest. At this very moment, you are rotating through space at more than 1,600 kilometers per hour, while the planet itself races around the Sun at nearly 108,000 kilometers per hour. Every sunrise you have ever witnessed was not the Sun moving across the sky. It was Earth, quietly, faithfully, turning toward the light. Tonight, we slow that motion down. We follow it gently, from the tilt of Earth's axis to the hidden rhythm of its orbit, and discover how every second of your life is written in movement. If this calm journey offers you even a small moment of peace, I'm grateful you're here. A gentle like or a soft tap on subscribe helps these quiet voyages continue. Now, let us begin with the first truth. Part 1. The Sun does not move. The Earth spins. Beneath your feet, without sound or sensation, the ground is turning. Every wall, every city, every ocean is being carried eastward as Earth spins on its axis, faster than the speed of sound at the equator. You never feel it, yet it never stops. At the same time, the entire planet is sweeping through space along its orbit around the Sun. Even in perfect stillness, you are traveling tens of thousands of kilometers each hour. And yet, the world feels calm. This illusion, motion without sensation, is one of the most elegant truths in physics. The Sun does not rise and set. Each dawn is simply Earth turning its face back toward the light. Our planet completes one full rotation in 23 hours, 56 minutes, and 4 seconds. Astronomers call this a sidereal day, measured against the distant stars. The familiar 24-hour day is slightly longer because Earth is also moving along its orbit, requiring just a little extra rotation for the Sun to return to the same position in the sky. That difference, only 4 minutes, quietly reshapes the heavens. Over a month, those minutes add up to hours. Over a year, an entire day. The stars above you tonight are not where they were last season, not because the universe shifted, but because you did. Long before modern instruments, ancient civilizations noticed these changes. They tracked shadows, charted constellations, and aligned temples so that sunlight would strike sacred stones on a single day each year. Today, NASA confirms the same rhythms using signals from distant quasars, measuring Earth's rotation to fractions of a millisecond. Yet this spin is not perfectly constant. Winds move. Oceans shift. Ice melts. Each change redistributes Earth's mass, subtly altering its rotation, like a figure skater adjusting speed by changing posture. After powerful earthquakes, scientists have measured changes in Earth's day length by mere microseconds. Small numbers, but immense precision. This steady rotation shapes everything: temperature balance, global winds, ocean currents, and the rhythm of life itself. Without it, Earth would be unrecognizable. Carl Sagan once said, "The Earth is a very small stage in a vast cosmic arena. But it is also a stage in motion, governed by the same laws of angular momentum that guide spinning electrons and rotating galaxies alike." At this moment, your body, the air around you, and the atoms within your bones all share the same motion. That is why you feel nothing. Everything that matters to you is moving together, perfectly synchronized. It is inertia at its most graceful. If Earth were to stop spinning suddenly, even for a second, the consequences would be catastrophic. Oceans would surge, winds would tear across continents, and equilibrium would collapse. Geophysicists study this impossible scenario to understand how rotation stabilizes worlds. Even Earth's axis is not fixed. It slowly wobbles in a cycle called axial precession, completing one turn every 26,000 years. This gentle motion shifts the poles and changes which star marks true north. Long ago, it was not Polaris but Thuban in the constellation Draco. Even direction itself is temporary. Daylight, time, north, all are born from motion layered upon motion. And yet, within all this movement, there is calm. Earth remains stable enough for life to breathe, grow, and sleep. The same physics that carries us through space also holds us in balance. So when you wake to the light tomorrow, remember this quiet truth: the Sun did not rise. You did. The world beneath you has never stopped turning. Yet it never moves at the same pace for long. Through space, Earth subtly accelerates and slows, following a path that shifts its rhythm day by day, season by season. And as this quiet journey continues, a deeper question waits. Part 2. Why the sun seems to change its pace. Have you ever noticed that the sun refuses to keep perfect time? Some mornings it arrives a little earlier than expected. Other evenings, it lingers, slipping below the horizon later than your clock predicts. Even the most precise watch cannot stay fully aligned with the sun, because the sun's motion across our sky is not uniform. But the change is not happening in the sun. It is happening in Earth. Our planet does not travel around the sun in a perfect circle. Instead, it follows a gentle oval, an ellipse, first understood through the work of Johannes Kepler. This slightly stretched orbit means Earth's distance from the sun is always changing, and with distance comes a change in speed. In early January, Earth reaches perihelion, its closest approach to the sun, at about 147 million kilometers. By early July, it arrives at aphelion, nearly 152 million kilometers away. The difference may seem small on a cosmic scale, yet it quietly reshapes the tempo of our sky. When Earth is closer, it moves faster, about 30.3 kilometers per second. When it is farther away, it slows to roughly 29.3 kilometers per second. That single kilometer per second difference stretches across millions of kilometers of orbit, subtly altering how the sun appears to move overhead. This shifting pace gives rise to something astronomers call the equation of time, a gentle correction that explains why solar time and clock time never perfectly agree. If you were to measure time only by the sun, marking the exact moment it crosses the sky's highest point, and compare it to your watch, you would always find a difference. Sometimes the sun runs ahead. Sometimes it falls behind. Over the course of a year, that offset can grow to as much as 16 minutes. Two forces create this effect. First, Earth's elliptical orbit changes its orbital speed. Second, Earth's tilted axis alters how the sun's path is projected across the sky through the seasons. Together, they cause the length of a solar day, the time between one noon and the next, to drift slightly above or below the familiar 24 hours. In early January, when Earth is moving fastest, each solar day stretches a little longer. In early July, when Earth slows, solar days shorten slightly. The difference is small, often just seconds, but those seconds accumulate. Over weeks, they shift sunrises and sunsets enough for careful observers to notice. This is why ancient sundials, though elegant and precise, never match modern clocks perfectly. The sun follows gravity, not human schedules. When scientists chart the sun's position at the same clock time every day for an entire year, a beautiful pattern emerges. The sun traces a looping figure-8 shape in the sky known as the analemma. You can find it printed quietly on some globes, drifting above the oceans, a signature of Earth's tilted axis and its uneven orbital speed. That figure-8 is not an error. It is a record of motion, a reminder that time itself bends gently with distance and velocity. This is also why the earliest sunset does not occur on the winter solstice, and the latest sunrise does not fall on the summer solstice. Those moments are shifted by weeks, shaped by Earth's changing speed and orientation in space. Modern missions like Gaia and NASA's orbital models now track these variations with astonishing accuracy, accounting even for the faint gravitational nudges of the Moon and neighboring planets. Together, they reveal Earth's orbit as something that subtly breathes, expanding and contracting in a rhythm billions of years old. And yet, you don't need spacecraft to feel it. If you have ever sensed daylight arriving later than expected on a winter morning, or lingering unexpectedly in summer, you have already felt the equation of time at work. It is the quiet clock of the cosmos, never repeating, never wrong. As one physicist once observed, the universe has no obligation to match our expectations. What feels irregular to us is, in truth, perfectly lawful, shaped by geometry, gravity, and motion. And that is why this matters. Because even the time ticking on your wrist is not absolute. It is built upon motion. And motion changes with distance and speed. The equation of time is the bridge between human order and celestial mechanics, a reminder that our calendars rest on a living, moving world. Long ago, sailors depended on this knowledge to find their place on Earth, knowing that a single minute of error could mean drifting dozens of kilometers off course. Time, it turns out, is not something we keep. It is something the universe allows us to borrow, one moving moment at a time. That is why, centuries ago, one quiet invention changed the fate of exploration. When John Harrison perfected the marine chronometer in the 18th century, humanity finally learned how to carry time across open oceans. With a clock that refused to drift, sailors could measure longitude, trace their position, and cross vast waters without being lost to uncertainty. Today, that same pursuit of precision lives far above you. Atomic clocks aboard GPS satellites measure time with astonishing delicacy. They correct not only for Earth's uneven motion around the sun, but also for something far stranger, the bending of time itself. According to Einstein's relativity, clocks tick at different rates depending on their speed and height above Earth. Without these corrections, GPS positions would wander by kilometers each day. So when your phone quietly tells you the exact time, it is not just reading a clock. It is blending centuries of astronomy with the insights of Kepler and Einstein, aligning your moment with the motion of a rotating, orbiting world. Your heartbeat is synchronized with celestial mechanics. The next time sunset feels slightly late or strangely early, remember, your clock is not mistaken. Earth is simply following its ancient, elliptical rhythm. The equation of time is more than mathematics. It is evidence that nature never repeats itself exactly. Even the most reliable cycles carry gentle variations within them. So tomorrow, when daylight arrives a little differently than expected, pause for a breath. You are witnessing a delicate balance, gravity, geometry, and motion woven together with time itself. And as this balance unfolds through the seasons, another question quietly rises. If time bends with motion, what are we truly measuring when we measure a day? Because if our clocks depend on Earth's imperfect spin, perhaps time is not a universal truth, but a shadow cast by movement. Part 3. Does time truly exist? Here is something quietly unsettling. There is no single moment shared by the entire universe. Even now, as you listen, this second is not happening everywhere at once. The faster you move, or the deeper you fall into gravity, the more slowly your clock runs compared to someone else's. This is not philosophy. It is physics. For most of human history, time meant sunrise and sunset, one full turn of Earth beneath the sky. But as our instruments sharpened, we discovered something unexpected. The rhythm of nature and the rhythm of clocks are not the same. In classical physics, time was thought to flow evenly everywhere. Isaac Newton imagined it as a steady backdrop, unaffected by motion or matter. That idea worked beautifully, until it didn't. In the early 20th century, Albert Einstein revealed that time is not separate from space. The two are woven together into a single structure called spacetime. According to his equations, time only exists in relation to motion. The faster something travels, the more slowly its time passes compared to a still observer. This effect, known as time dilation, has been tested again and again. In the 1970s, atomic clocks flown around Earth returned slightly out of sync with those left behind, off by billionths of a second, exactly as Einstein predicted. Today, the same effect is essential for satellite navigation. Orbiting clocks tick differently than those on the ground, and without correction, our digital maps would slowly drift out of reality. Even gravity reshapes time. The stronger the gravitational field, the slower time flows. Near extremely massive objects, moments stretch and bend. Around black holes, seconds can unfold into hours. Observations of distant galaxies and massive cosmic structures confirm that time itself is influenced by mass. This means a second is not universal. It is local. What we call a moment here on Earth exists only under our planet's gravity and motion. Somewhere else, that same second would be longer, or shorter. There is no master clock governing the universe. At the smallest scales, time becomes stranger still. In quantum physics, particles do not move smoothly from one moment to the next. They exist in probabilities, where time seems to pause between interactions. Some experiments suggest that time may not be fundamental at all, that it emerges from deeper physical processes, just as temperature emerges from the motion of atoms. If all motion ceased, if every particle, wave, and field froze, physics tells us that time would vanish with it. Because time is not a thing. It is a measure of change. Without change, there is no before and after. Even the most precise cosmic measurements confirm this. Observations of billions of stars reveal constant motion everywhere. There is no absolute stillness in the universe. Every object experiences its own proper time, shaped by speed and gravity. Astronauts aboard the International Space Station age slightly differently than those on Earth. Their clocks tick more slowly by tiny amounts, small but real. Even standing upright changes how fast you age. At extreme precision, your head moves through time faster than your feet. As one physicist quietly observed, everywhere is local time. This realization transforms how we understand reality. Time is not a river flowing past us. It is a dimension that stretches and curves with energy and motion. It is flexible, relational, alive. If motion defines time, then the universe cannot stop. Change is existence itself. And that is why time endures, not as a universal truth, but as a reflection of movement. When telescopes gaze deep into space, they are not just looking across distance. They are looking backward through time. Light carries its history with it. Every distant galaxy is a memory arriving late. So the universe does not move through time. Time moves because the universe does. And tonight, as Earth continues its quiet spin beneath you, you are not just resting within time. You are part of what creates it. Every particle of light carries a memory. Each photon arrives stamped with the history of its journey. Its energy, its motion, its slow fading across space. When we look outward into the universe, we are not watching events unfold in real time. We are reading an archive. The sky is a library of moments that have already passed. So when we ask whether time truly exists, modern physics offers a quiet answer. Not as a separate, universal substance. Time is not something the universe contains. It is something that emerges, locally, relationally, through motion and gravity. This understanding reshapes how scientists describe the cosmos. The equations of cosmology do not track isolated moments. They describe intervals, relationships between events in spacetime. Even the commonly cited age of the universe, about 13.8 billion years, is not an absolute number everywhere. It is measured relative to a specific frame of reference, the faint afterglow of the Big Bang known as the cosmic microwave background. In other words, age itself depends on where and how you measure it. As Neil deGrasse Tyson once remarked, the universe has no concern for what time it is where you happen to be. For most of human history, we believed time was something we simply recorded. Now we understand it differently. Time is something we produce, through movement, mass, and observation. That realization is quietly humbling. The passage of time is not an external rule imposed on reality. It is a consequence of everything that moves within it. Tomorrow, when you glance at a clock, consider this. The seconds you see are not fixed. They depend on your planet's rotation, your height above its surface, and your velocity through space. Each ticking moment reflects your position in the universe. And as we follow that ticking more closely, another curiosity appears. If time itself varies from place to place, then what does something as ordinary as noon really mean? Part 4. Noon is not the same everywhere. At this very moment, somewhere on Earth, a clock reads 12. Yet the sun is not standing at its highest point in that sky. In fact, for most places on the planet, it almost never does. The clock may announce midday, but the heavens tell a different story. This quiet mismatch between human time and solar motion is one of the most overlooked consequences of how Earth moves through space. It also marks the point where natural time slowly gave way to artificial time. In astronomy, true noon has a precise definition. It is the instant when the sun crosses your local meridian, the invisible line running north to south through your position. At that moment, the sun reaches its daily peak in the sky, and shadows shrink to their shortest length. But Earth's rotation is not uniform, and its axis is tilted by 23.4 degrees. Because of this, the sun rarely aligns with 12 o'clock on your watch. Move just 1 degree east or west, about the distance of a short drive, and solar noon shifts by roughly 4 minutes. Even neighboring towns experience the sun's highest point at slightly different times. Before mechanical clocks, this wasn't a problem. Communities lived by the sky. Noon happened when it happened. The sun was the schedule. That changed in the 19th century. As railways and telegraphs stitched distant cities together, local solar time became impractical. Trains could not safely operate if every town defined midday differently. So in 1884, an international agreement divided Earth into 24 time zones. A single reference line, the prime meridian, was set through Greenwich, England. Standard Time brought order. But it also concealed the planet's natural irregularities. When your device updates the time as you cross a border, it is obeying a human system, not the sun. In some regions, the difference is subtle. In others, it is striking. Large countries may span several natural solar zones but follow only one official time. As a result, clock noon can arrive long before, or long after, the sun reaches its highest point. In parts of the world, that difference can approach 2 full hours. Even solar noon itself is not constant. Because Earth follows an elliptical orbit and changes speed throughout the year, the sun's apparent position drifts. This creates what astronomers call the equation of time, the shifting gap between true solar time and average clock time. Over a year, solar noon can slide by as much as 16 minutes. If you were to mark the sun's position at the same clock time every day, the points would trace a looping figure 8 in the sky. This shape, known as the analemma, appears on some old globes, a quiet signature of Earth's tilt and orbital motion combined. Modern missions like Gaia and NASA's orbital models can predict these variations with astonishing accuracy, centuries into the future. The mechanics are precise, even if the experience feels uneven. Yet our daily lives run on averages. Every clock you use is synchronized to coordinated universal time, maintained by atomic oscillations far steadier than Earth's rotation. But Earth itself slowly loses rotational energy, tugged by the moon through tidal friction. To keep human time aligned with solar reality, an extra second is occasionally added, a leap second, to prevent the drift from growing too large. This careful adjustment is a form of cosmic housekeeping, a way to keep our schedules loosely tethered to the sky. Still, that tether is thinning. As atomic clocks grow ever more precise, scientists debate whether leap seconds should be abandoned altogether. If they are, clock time will slowly drift away from solar time, by minutes, then hours, over centuries. In truth, that separation has already begun. Artificial light, global networks, and digital timekeeping have loosened our connection to the sun's rhythm. But the natural world continues unaffected. The sun still crosses every meridian once per day, whether we notice or not. When your clock reaches 12 tomorrow, remember this. Noon is not a universal moment. It is an agreement, a convenience layered over a moving planet. The universe did not adjust itself to match your schedule. We adjusted the universe to fit ours. And as we look closer at that adjustment, something deeper becomes clear. Earth is not merely spinning in place. It is drifting, carried along invisible currents of motion far larger than a single day. Part 5. Where is Earth really going? Right now, even as your body rests in stillness, Earth is on a long, graceful journey. The floor beneath you, the sky above you, and the sun that warms the day are all moving together through space at astonishing speed. You don't feel it, not because it isn't happening, but because everything you know is moving as one. Most of us learn early that Earth turns once on its axis in just under 24 hours. We also learn that it travels around the sun in a yearly loop, rushing along its path at more than 100,000 kilometers per hour. These motions are real, but they are only the nearest layers of a much deeper drift. Far beyond Earth's daily spin and yearly orbit, the entire solar system is sliding through the Milky Way. The Sun, along with its planets, moons, and debris, circles the galaxy's core, an unseen heart located tens of thousands of light-years away toward Sagittarius. Hidden there is Sagittarius A*, a supermassive black hole whose gravity quietly governs the dance. One full orbit around this galactic center takes about 230 million years, a span known as a galactic year. Over that immense time, Earth travels distances so vast they stretch beyond intuition. NASA describes this motion simply. Our solar system sweeps around the Milky Way at roughly 220 kilometers per second. And yet, the stars appear calm and fixed, because they share the same silent flight. Still, even the Milky Way is not at rest. Careful measurements from the European Space Agency's Gaia mission reveal that our galaxy is drifting toward a distant region called the Great Attractor, hidden between the constellations Leo and Virgo. This is not a single object, but a massive gravitational basin within the Laniakea supercluster, a structure containing tens of thousands of galaxies spread across hundreds of millions of light-years. Like water flowing downhill, galaxies move along invisible slopes carved by gravity. And even this flow is not the end. Beyond the Great Attractor lies the pull of the Shapley supercluster, suggesting that motion continues on scales larger than imagination. There is no final resting place, no absolute still point in the cosmos. Everything moves in relation to something else. While you sleep for a single night, Earth completes a large fraction of its rotation, glides nearly 1 million kilometers along its path around the Sun, and is carried millions more through the galaxy itself. You feel none of it, because motion shared feels like stillness. Air, oceans, continents, and your own body belong to the same moving frame. This is a quiet rule of physics. Constant motion cannot be felt without change. Only acceleration announces itself. Smooth, steady travel passes unnoticed, like a boat drifting on a calm sea. Gaia has shown that even the Sun's galactic path gently rises and falls, weaving above and below the Milky Way's disk in a slow wave that takes tens of millions of years to complete. Some researchers wonder whether these passages through denser regions of space may influence long-term events on Earth, such as comet encounters, though the evidence remains subtle. Zooming farther out, the Milky Way belongs to a small family called the Local Group, alongside Andromeda and Triangulum. Gravity is slowly drawing these galaxies together. In several billion years, the Milky Way and Andromeda will merge into a single, larger galaxy, a future already hinted at by Andromeda's measured approach. Beyond even that, the Local Group is part of Laniakea, and the entire structure moves relative to the cosmic microwave background, the faint afterglow of the Big Bang. This motion leaves a delicate fingerprint in the sky, a temperature imbalance that confirms we are never truly still, even against the oldest light in the universe. Every second carries us into new regions of space. We never return to the same cosmic address. The stars you see tonight are already different from what ancient skies once held. Some of their light began its journey before human history began. Astronomy teaches this gently. Motion is not an interruption of existence. It is existence itself. From electrons circling atoms to galaxies drifting along cosmic filaments, everything belongs to nested orbits within larger ones. So if we ask where Earth is going, science offers a calm answer. We are moving within movements, carried by gravity through structures still being revealed. The destination is not a point, but a flow. And that is the quiet wonder to rest with tonight. The ground feels steady only because we travel together. Part 6. A day isn't really 24 hours. Crescent Moon. Part 6. A day is not quite what we think. Every clock on Earth tells a story that is almost true. We grow up believing that a day lasts exactly 24 hours, neat and complete. But the planet beneath us keeps a slightly different rhythm. In astronomical terms, Earth completes a full spin not in 24 hours, but in 23 hours, 56 minutes, and 4 seconds. This interval is called a sidereal day, the true measure of Earth's rotation against the distant stars. So where do the missing 4 minutes come from? The answer lies in layered motion. As Earth turns on its axis, it is also gliding along its path around the Sun. During a single rotation, Our planet travels millions of kilometers along its orbit. By the time Earth has completed one full spin relative to the stars, the Sun has shifted slightly in the sky. To bring the same longitude back into alignment with the Sun, Earth must rotate a little more, about 1 extra degree. That subtle adjustment takes roughly 4 additional minutes. Those extra minutes create what we call the solar day, the familiar 24 hours from one noon to the next. The stars, however, do not move with us in this way. They provide a stable cosmic backdrop. That is why sidereal time runs slightly faster than solar time, quietly advancing beneath our daily routines. This difference may seem small, but it shapes the sky itself. Night after night, the stars rise a little earlier. Over a month, the shift becomes obvious. Over a year, it completes a full cycle. This is why different constellations rule different seasons, why Scorpius dominates warm summer nights, while Orion returns in winter's cold air. Astronomers live by this deeper clock. Ground-based telescopes, space observatories, and tracking systems are synchronized not to human time, but to sidereal time. Their instruments follow Earth's true rotation so precisely that even a single second of error could blur distant galaxies into softness. Time, it turns out, has layers. One layer organizes human life, workdays, calendars, sleep. Another governs the geometry of the universe. If you tried to live by sidereal time alone, your days would drift earlier by 4 minutes each sunrise. After months, midnight would arrive at noon. After a year, the cycle would quietly reset. Even this rhythm is not perfectly steady. Earth's spin is slowly changing. The gravitational pull of the moon tugs at our oceans, raising tides that act like cosmic brakes. Over immense spans of time, this friction slows the planet's rotation. Hundreds of millions of years ago, days were shorter. There were more of them in a year. Ancient corals and layered sediments still carry the record of those faster spins, like fossilized clocks. Today, the change is tiny, mere milliseconds over centuries, but it is measurable. Atomic clocks notice what our senses cannot. To keep global time aligned with Earth's motion, scientists occasionally insert a leap second, gently stitching human time back onto planetary reality. All of this matters because motion must be known precisely. Satellites, spacecraft, eclipses, and interplanetary journeys depend on Earth's exact orientation in space. Even a small timing error can grow into vast distances when projected across the solar system. So when you notice the stars appearing earlier each night, you are seeing the sidereal clock at work, the quiet heartbeat of Earth's true rotation. A day, then, is not a fixed thing. It is a balance between spinning and traveling, between turning in place and moving forward. The familiar 24 hours are not a mistake, but a convenience layered atop a deeper cosmic rhythm. The universe keeps its own time. We simply borrow a version that fits our lives. And that gentle mismatch, those 4 extra minutes, exist because Earth is never still. Each rotation carries us farther along our endless orbit around the Sun. But there is another detail in Earth's motion, just as subtle, just as powerful. A small lean, a quiet angle that changes everything. Part 7. Tilted by 23.4 degrees. If Earth stood perfectly upright, like a balanced top, the world would be strangely uniform. No summers. No winters. The equator would always burn. The poles would remain locked in ice. Every sunrise would feel the same as the last. But Earth does not stand straight. Our planet is tilted by 23.4 degrees, a slight lean that transforms climate, weather, and life itself. This angle, called axial tilt, allows sunlight to shift north and south through the year, breathing warmth and cold across the globe. Because of this tilt, seasons are born. Oceans move. Winds change. Ice grows and retreats. Crops rise and fall. Monsoons arrive. Entire ecosystems follow a rhythm written not in days, but in angles. A small tilt. A moving planet. And from these quiet motions, the living world emerges. As you rest now, imagine that tilt holding steady beneath your feet, guiding the slow dance of light and shadow across Earth's surface. Motion shaping time. Time Shaping Life. Part 7. The Power of a Small Lean. In astronomy, 23.4 degrees sounds insignificant. Just a tilt. A fraction of a circle. Yet this single angle has shaped climates, ecosystems, and the entire history of life on our planet. Earth does not spin upright. Its axis leans gently as it travels around the sun, and that lean never changes direction in space. As the planet moves along its slightly stretched orbit, one hemisphere tips toward sunlight while the other tips away. Months later, they trade places. When a hemisphere leans toward the sun, sunlight strikes the ground more directly. The same energy is focused onto a smaller area, warming land, oceans, and air. This is summer. Half a year later, the angle reverses. Sunlight arrives at a slant, spreading thin, losing strength. Winter follows. What matters most is not distance, but direction. In fact, Earth is closest to the sun during northern winter, in early January. Yet cold dominates the north because that hemisphere is tilted away. Distance plays only a minor role. Geometry does the real work. This simple angle organizes the planet into zones. Near the equator, sunlight arrives almost straight down all year long, keeping temperatures steady. Toward the poles, light schemes across the surface, delivering less warmth. At extreme latitudes, the tilt creates something even stranger: weeks where the sun never sets or never rises at all. Above the Arctic Circle, summer brings endless daylight. Winter brings unbroken night. Both are direct consequences of a leaning world. But the tilt itself is not frozen in time. Over thousands of years, Earth's axis slowly traces a gentle circle in space, a motion called precession. At the same time, the tilt angle subtly shifts, drifting between about 22 and 24.5 degrees. These slow variations, driven by gravitational interactions with the Moon and other planets, form part of what scientists call the Milankovitch cycles. When the tilt increases, seasons grow more extreme. Summers intensify. Winters deepen. When it decreases, seasonal contrasts soften, and ice sheets gain ground. Over tens of thousands of years, these changes help trigger the advance and retreat of ice ages. Right now, Earth sits near the middle of that range. A fortunate balance. Enough variation to drive weather, winds, and ocean currents, but not so much that climate becomes chaotic. This balance may owe its stability to the Moon. The Moon's gravity acts like a steadying hand, preventing Earth's axis from tipping wildly. Without it, simulations show the tilt could swing dramatically, pushing the planet through violent climate shifts that would make long-term life difficult, if not impossible. So much depends on that quiet companion in the sky. At the solstices, the tilt reveals itself most clearly. In June, the northern hemisphere leans fully toward the sun. In December, the southern hemisphere does. Between them lie the equinoxes, moments of balance when day and night briefly share equal time across the globe. From this choreography emerge deserts and rainforests, monsoons and jet streams, migration routes and growing seasons. Shift the tilt by only a couple of degrees, and entire ecosystems would reorganize. Ice would surge or vanish. Winds would change direction. Familiar climates would disappear. Every harvest, every snowfall, every leaf that turns color traces back to that single number. If you could watch Earth from far away, you would see a spinning sphere leaning gently as it circles the sun, painting its surface with moving bands of light and shadow. That lean is not a flaw. It is the architecture of habitability. When sunlight warms your skin, it does so not because the sun moved closer, but because Earth leaned just enough to meet it. And that small, steady angle, 23.4 degrees, may be one of the most precious coincidences in the universe. Part 8. Leap years are not mistakes. While Earth's tilt sculpts the seasons, time-keeping struggles to keep up. A year, despite what calendars claim, is not exactly 365 days long. Earth needs a little more time, just under 6 extra hours, to complete one full orbit around the sun. That fraction seems harmless. But nature never ignores fractions. Without correction, the calendar would slowly drift away from the sky. Spring would slide earlier. Winter would creep into summer months. In only a few centuries, seasons would no longer match their names. The solution is subtle: an extra day. Every 4 years, February gains one quiet addition. Not as a convenience, but as a correction. A way to stitch human time back onto planetary motion. Ancient civilizations noticed this drift long before atomic clocks existed. Early calendars slipped against floods, harvests, and stars. Reforms followed. Adjustments were made. Eventually, the modern system emerged, a calendar tuned not to perfection, but to precision. Even today, the work continues. Tiny mismatches accumulate. Corrections are applied. Time is gently nudged back into alignment. Because Earth never moves in whole numbers. It tilts. It wobbles. It orbits with fractions and angles. And our calendars, like our clocks, are quiet compromises, human attempts to keep pace with a planet that never repeats itself exactly. As you rest now, imagine Earth continuing its steady lean, its careful orbit, its endless corrections. Seasons arriving on schedule. Years slipping into place. Time holds together not because it is simple, but because it is constantly adjusted. And that, too, is part of the quiet beauty of a moving world. Globe showing Europe-Africa sparkles. The careful design of leap years matters far beyond calendars on a wall. At NASA's Jet Propulsion Laboratory, this precision becomes essential. Spacecraft do not forgive small mistakes. A drift of even minutes per year can grow into thousands of kilometers when plotting interplanetary paths. Planets arrive late. Windows close. Trajectories miss their mark. To avoid such errors, astronomers often step outside ordinary calendars altogether. They use Julian dates, a continuous count of days stretching back to January 1st, 4713 BCE, a system that ignores months and leap years entirely, flowing without interruption. It is time stripped to its purest sequence. Yet for everyday life on Earth, the Gregorian calendar remains our most faithful tool. Its elegant rules keep the average year astonishingly close to reality, drifting from Earth's true seasonal cycle by only seconds each year. At that rate, it would take more than 3 millennia for the calendar to slip by a single day. Even so, perfection remains unreachable. Earth itself refuses to cooperate fully. The planet's rotation slows, almost imperceptibly, as the moon draws energy away through tidal friction. Days lengthen by tiny fractions of a millisecond each century. Over long spans of history, this gradual change forces science to intervene again. That responsibility falls to organizations that quietly watch the planet turn. They compare atomic time, measured by the vibrations of cesium atoms, with Earth's actual rotation. When the two drift too far apart, a correction is made. A leap second is inserted. A pause. A breath. Seconds, like days, are adjusted. Hidden beneath every schedule, every appointment, every launch countdown, is a constant negotiation between mathematics and motion. Time, as we live it, is not fixed. It is maintained. Every leap day is a reconciliation. A moment when humanity gently realigns itself with the orbit that carries us. February 29th is not an anomaly. It is a reminder that Earth keeps imperfect time, and that we choose to follow it anyway. Even the James Webb Space Telescope depends on these corrections. Its observations are scheduled months ahead, calculated with exquisite sensitivity to orbital timing. Miss a correction, and a distant galaxy might slip out of view. So that single added day reaches from birthdays to black holes, from classrooms to cosmic horizons. When you notice a leap year on the calendar, remember what it represents: hours of accumulated drift, quietly returned to the universe. Precision not as rigidity, but as care. Timekeeping, like science itself, is a living practice, refined, corrected, and humbled by motion. And within that rhythm, another question begins to rise. Not how we measure time, but how far we travel while it passes. Part 9. The journey you never feel. You have never been still. Not for a single second of your life. Even now, as your body rests, You are moving faster than any vehicle humanity has ever built. The sensation of stillness is a gift of shared motion, not a lack of speed. From the moment you were born, the ground beneath you was already spinning. Earth's surface carries you eastward at over 1,600 kilometers per hour. At the same time, the planet sweeps around the Sun at more than 100,000 kilometers per hour. And the Sun itself moves, guiding its family of planets through the Milky Way at nearly 800,000 kilometers per hour. Beyond that, the galaxy drifts toward vast gravitational structures, unseen yet undeniable. Every layer of motion stacks atop another. During a single night of sleep, you travel millions of kilometers through space. Over the course of a lifetime, the distance becomes almost impossible to imagine. Billions upon billions of kilometers traced silently through the dark. And yet, you feel none of it. Why? Because everything moves together. The air, the oceans, the continents, your own body, all share the same velocity. Physics calls this an inertial frame. Within it, constant motion disappears. Only changes announce themselves. This is why astronauts aboard the International Space Station feel weightless. They are not beyond gravity. They are falling endlessly around Earth, sharing its motion so perfectly that gravity becomes invisible. You experience the same principle, gently, constantly, without noticing. Data from ESA's Gaia mission reveals that even the Sun's path through the galaxy is not flat. It rises and falls, oscillating through the galactic plane over millions of years. Every human life traces a tiny segment of that vast wave. If you could step far outside the galaxy and look back, you would see a glowing ribbon of motion. Planets circling a star. The star drifting through spiral arms. The galaxy itself sliding through the cosmic web. Every person who has ever lived is embedded in that motion. In a single day, Earth carries you tens of thousands of kilometers around its axis, millions more along its orbit. And far beyond that, the solar system advances deeper into the Milky Way. Multiply that by years, by decades, by a lifetime. Still, you pour water into a glass without spilling it. You light a candle without its flame bending. Motion hides itself when it is shared. This is one of the quietest, most beautiful truths of physics. Movement does not announce itself. It simply happens. Earth wobbles slightly as it spins. Its axis traces slow circles. Gravitational nudges from the moon and planets introduce tiny variations, measured in milliseconds, yet precise enough to guide spacecraft across the solar system. Nothing stands still. Not planets. Not stars. Not you. The feeling of rest is not the absence of motion. It is harmony within it. And as Earth continues its journey, spinning, tilting, orbiting, it carries you along, gently, endlessly, through a universe that never pauses. As this motion continues, another subtle rhythm waits ahead. One tied not to distance, but to balance. To how Earth keeps itself upright while everything else pulls. So while your body feels perfectly still, technology can detect your motion with astonishing precision. Atomic clocks aboard GPS satellites tick at slightly different rates than clocks on Earth's surface. The reason is pure relativity. Their speed through space and their weaker gravity cause time itself to flow differently. Without Einstein's corrections, GPS locations would drift by nearly 10 kilometers every single day. Every navigation system, every aircraft route, every ship crossing the ocean depends on accounting for this invisible dance between motion and time. Our feeling of stillness is not just an illusion. It is a fragile equilibrium. Life exists because motion is shared. If Earth were to stop spinning instantly, the oceans and atmosphere would keep moving at over 1,600 kilometers per hour, scouring continents clean. The calm we experience comes from co-motion, everything traveling together in balance. Physicists call this a co-moving frame, the same principle that allows galaxies to expand with space itself, carried along rather than torn apart. On cosmic scales, nothing is truly at rest. The universe is not built from stationary islands. It is a woven structure of systems moving together, frictionless at their largest scales. As you age, you are not merely passing through time. You are being carried through space itself. Every moment of your life traces a unique path that will never repeat. The place in the galaxy where you first opened your eyes, where you first stood, where you first looked up at the night sky, now lies billions of kilometers behind you. Each memory occupies a different location in the Milky Way. Astronomers describe positions using galactic coordinates, and data from ESA shows that our solar system is moving at several kilometers per second toward a region near the constellation Hercules. By the time you finish listening tonight, you will already be hundreds of thousands of kilometers closer to that distant direction. If your life left a visible trail, it would not be a straight line. It would be a slow spiral, wrapping around the sun, threading through the galaxy like a luminous filament woven into the Milky Way's fabric. Even the James Webb Space Telescope, orbiting far beyond Earth, drifts within that same current. It looks backward in time, capturing ancient light, while moving forward through space alongside the planet that created it. Everything we build, everything we observe, shares this motion. Yet because our senses evolved inside it, we experience stability. Stillness becomes the default feeling inside a universe that never stops traveling. Carl Sagan captured this gently when he reminded us that we are passengers on a small blue world in a vast darkness. That world does not hover. It flies. Its motion defines our days and nights, our seasons and years, even our sense of time itself. Tonight, when you close your eyes, consider this. During 8 hours of sleep, you will travel nearly the distance between Earth and the Moon without moving a muscle. When you wake, you will be somewhere new in the galaxy, carried there by a planet that spun, orbited, and drifted millions of kilometers onward. So yes, stillness is an illusion. But it is a beautiful one. A quiet design that allows life to exist safely inside constant motion. And yet, even as we learn to measure that motion, our attempts to keep time have not always gone smoothly. Once, in our effort to correct the calendar, we did something extraordinary. We erased days. Part 10. The Days That Vanished. Imagine going to sleep one night and waking to discover that 11 days of your life no longer exist. Not lost to disaster. Not erased by war. Simply removed. That is exactly what happened in September of 1752. In the British Empire, people went to bed on September 2nd and woke up on September 14th. 11 days disappeared overnight. No sunrise marked them. No memories were made within them. This strange moment was not magic. It was mathematics. The story begins centuries earlier with the Julian calendar, introduced by Julius Caesar in 46 BCE. Roman astronomers calculated that a year lasted 365.25 days and added one leap day every 4 years to correct the fraction. For a time, the system worked beautifully. But it was slightly wrong. The true tropical year, the cycle that carries Earth from one equinox to the next, lasts about 365.24219 days. That difference, just 11 minutes per year, was small enough to hide. But it accumulated silently. Like grains of sand slipping through an hourglass, the error grew. After 128 years, the calendar was ahead of the sky by one full day. After 15 centuries, the drift reached nearly 10 days. By the 1500s, the spring equinox no longer arrived around March 21st. It was occurring closer to March 11th. The heavens themselves had slipped out of alignment with human dates. For astronomers and scholars, this was alarming. The equinox governs agriculture, navigation, and religious observances. The sun was no longer obeying the calendar. So in 1582, Pope Gregory XIII, guided by astronomer Christopher Clavius, ordered a correction. The solution was elegant but drastic. 10 days were removed to realign the calendar with the sky, and new leap year rules were introduced to prevent the error from returning. Some countries adopted the change immediately. Others resisted for generations. When Britain finally accepted the Gregorian calendar in 1752, the correction had grown to 11 days. And so, those days were erased. History skipped forward to catch up with the Earth. People protested. Some believed time itself had been stolen. But nothing was taken. Humanity was simply synchronizing with a planet that never stopped moving. Those missing days remind us of something profound. Timekeeping is not absolute. It is an ongoing agreement between human order and cosmic motion. And every correction we make is an admission of humility, because the Earth does not adjust to us. We adjust to the Earth. As our quiet voyage through time and motion draws to its gentle close, consider this: the Gregorian calendar was humanity's way of listening carefully to the rhythm of the cosmos. By skipping 10 days in 1582, Thursday, October 4th followed immediately by Friday, October 15th, Catholic Europe realigned its clocks with the Earth's orbit. But not everyone agreed. Protestant nations clung to the old Julian system. England and its colonies waited until 1752, when the calendar was 11 days behind. September 2nd was followed by September 14th. 11 days vanished. Legend has it that mobs demanded, "Give us back our 11 days." Though historians think the uproar was exaggerated, confusion and mistrust were real. Birthdays shifted, contracts were rewritten, and even George Washington ended up celebrating 2 birthdays. Yet beneath the chaos lies a profound truth: time is not absolute. It is a collaboration between the planet's motion and human precision. NASA calls the Gregorian reform a masterstroke, restoring harmony between human time and celestial time. Today, the system remains the international standard, averaging 365.2425 days per year, just 26 seconds longer than the tropical year. That tiny fraction means it would take over 3,300 years for the calendar to drift by a single day. Yet even this incredible precision isn't permanent. Earth's rotation slows due to tidal friction from the Moon, adding about 1.7 milliseconds to the day per century. Over millennia, further adjustments will be needed. That's why organizations like the International Earth Rotation and Reference System Service occasionally add leap seconds to keep atomic time aligned with planetary motion. The same principle that once demanded 11 lost days in 1752 now operates invisibly in fractions of a second. Without it, clocks, satellites, and even our phones would gradually fall out of sync with sunrise and sunset. Every aspect of civilization, from farming to navigation, from astronomy to spaceflight, depends on measuring Earth's spin with remarkable accuracy. Even spacecraft rely on this precision. ESA engineers calculate launch windows based on Earth's exact rotation and orbit around the Sun. A single second off could send a probe hundreds of kilometers off course. Those 11 days lost in 1752 were not mistakes, they were the price of realignment. Humanity recalibrated its clock to match the true heartbeat of the solar system. Now, atomic clocks measure time with mind-boggling exactness, using cesium-133 atoms vibrating at 9,192,631,770 cycles per second. Even the slight difference in gravitational pull between a mountaintop and a valley produces measurable effects, predicted by Einstein's theory of general relativity. Gravitational time dilation means clocks tick faster at higher altitudes, slower in deeper valleys. The lost days, the added seconds, the constant adjustments, they all tell the same story. Timekeeping is a living craft, continually refined to stay in step with a planet that never stops moving. Neil deGrasse Tyson reminds us, the universe is under no obligation to make sense to you. Yet we build systems to make sense of it anyway. Systems that predict eclipses, track planets, and launch spacecraft billions of kilometers away with mathematical precision. When the British Empire erased those 11 days, it wasn't rewriting history. It was synchronizing with reality. And in doing so, it joined a lineage of astronomers, mathematicians, and engineers who have spent millennia ensuring humanity stays in rhythm with the cosmos. Every date, every clock, every schedule exists because of this constant calibration. From the 11 vanished days to the leap seconds of today, our timekeeping is always chasing a planet that never stops turning. Carl Sagan once said, "We are like butterflies who flutter for a day and think it is forever." Yet even in that fleeting flutter, the Earth beneath us spins, adjusts, and corrects its measure of motion against the stars. So when you see your calendar, notice February 29th, or recall the 11 days once lost, know this: it is all part of the same story. A world in motion, measured and honored by human curiosity. And as this chapter closes, let it remind you, every tick of every clock, from sundials to atomic oscillations, is a conversation between Earth and the universe. Rest now. Drift into dreams beneath the vast sky. Even in stillness, we are always moving. Your night is a voyage, your sleep a silent journey across the heavens. May it be peaceful, deep, and filled with the gentlest of dreams.